Welcome to 35th lecture on numerical analysis, and in this lecture we will study numerical solution of ODEs, ordinary differential equations. We'll see how to solve ODEs, the first order ODEs, the first order ordinary differential equations using numerical techniques. There are a number of techniques, but in this lecture we will study the famous Taylor series method. Right, an ODE is of the form like this, that we have dy over dx, which we also write as y prime of x is equal to some function of x and y, where y is the function of x and we have to find y as a function of x. This is the target. So this is the target, you have to find it, y as a function of x given this differential equation. Right, so and Taylor series is also a revision. We have studied Taylor series before. It's also a revision. A Taylor series is it looks like this, that we want to find y as a function of x. We must know y at some starting point where x naught is some starting point, starting value of x, and then x minus x naught dot 1 factorial times y prime, which y prime is dy by dx evaluated at the starting point, and then we keep on going like this. We have factorial terms growing in the denominator, and in the numerator we have the difference term whose power is increasing by 1 for each new term, where x naught is the starting value. And if x naught is equal to 0, in most of the cases we will be dealing, we'll have x naught is equal to 0. Then equation 1, this equation becomes, if you put x naught is equal to 0 in this term, in this equation, this becomes y of 0 instead of y of x naught, because we have put x naught is equal to 0, the special case, and x minus x naught is where x naught is 0, this is x, and then x squared, then x cubed, then x to the 4, and this y prime of x naught becomes y prime of 0, y prime of x naught becomes y prime of 0, and so on. So the technique is that given our differential equation and an initial condition y of x naught, we put y of x naught, y prime of x naught, y prime of x naught in 1 in this equation, and we find y of x. So if we are given y of x naught, the initial condition, and then we can compute y prime of x naught, y prime of x naught, and so on. We can compute y of x, and if the initial condition is 0, x naught is equal to 0, the initial condition is 0, then we put y of 0, y prime of 0, y prime of 0, and so on in equation number 2, this equation. With equation number 2 is a special case of equation number 1, where x naught is 0, the starting point is 0. So this equation seems a bit simpler than this equation, because equation number 2 is a special form of equation number 1, where x naught is equal to a 0. Right, so let's solve an example that given a very simple differential equation, y prime of x is dy by dx is 3y, and we are also given an initial condition that y of 0 is of 1. So if we have this, then find y of x is, then we have to find y of x and y of 1. So we have to find y of x in general, and then we have to find y of 1. So we'll use equation number 2 because x naught is 0. This is x naught. This x naught is given to be 0 in this case, therefore it would be this. So we will be using equation number 2, the simpler equation. That's right. So y of x would be y of 0 plus x over 1 factorial y prime of 0, and then we keep on going. So given y of 0 is of 1, so given this initial condition, so we know the first thing, y of 0 is equal to 1. Then the second term, y prime of 0. To find y prime of 0, we'll start with the given ODE. The given ODE is y prime of x is 3y. So we'll start from here, and then this y is actually y of x, and then we put x equal to 0, then y prime of 0 is 3y of 0, and y of 0 is of 1 given as an initial condition. So y prime of 0 becomes 3. To find y prime prime of 0, let's start with y prime of x is equal to 3yx, the given differential equation. We differentiate on both sides. This becomes y prime prime instead of y prime, becomes y prime prime because we differentiated, and this becomes 3 by dx of 3yx, and we can take 3 out here, then it becomes 3 by dx of y of x or y prime of x. So y prime prime of x is 3y prime of x, and then y prime prime of 0 is 3y prime of 0, and y prime of 0 is 3. So we put 3 here, it becomes 9. So y prime prime of 0 is 9. So we keep on going. Y prime prime of x is 3y prime of x, this one. We differentiate on both sides, becomes y triple prime of x is 3 y prime prime of x, and putting x is equal to 0, so y 3 primes of 0 is 3y prime prime of 0 is 3 times y prime prime of 0 is this 9. So it becomes 9 3s are 27, and then we can start from y 3 primes of x is equal to 3y prime prime of x, and we can again differentiate it, and then becomes y 4 prime of x is 3y 3 primes of x, and putting x is equal to 0, y 4 primes of 0 is 3y 3 primes of 0, 3 times 27 is 281, and then we plug everything in equation number 2. We start with 4 terms, we can go on with 5 6 or 7 terms, with any number of terms we want. So if we go on further with more terms, the answer would be more accurate. So y of x, putting everything in equation number 2, gives us this, and we put it here, x 3x 9 by 2 x squared 27 by 3 factorial. This is 2 factorial. In fact, 2 factorial is equal to 2. So, and if we compute y of 1, we replace x with a 1, and the answer comes out to be 16.375. But if you use the exact solution, this becomes y prime of x is given to be 3y is 1 over 3y. If we take 3y here, take dx here, this becomes log of y is 3x plus some constant c, and since y of 0 is a 1, therefore c is a 0. We can prove that c is a 0 because y of 0 is a 1. So c is 0. So y is e to the 3x. So y of x is e to the 3x, then y of 1 is 20.07. So we see your answer is 20.07. This is the exact answer, and I have written it as a question here. Why is the exact solution very different from the approximate solution that we have computed using Taylor series method? The answer is 16.375 here, but the exact answer is 20.07. Why is it different? Because we have used only 4 terms. If we would have used 4 terms, the answer would be 18.4. If you would have used 6 terms, the answer is 19.4, and if you use 7 terms, the answer is 19.8, and you keep on going. If you use 10 terms, the answer is exact 20.07. So how can you do that? Doing it by hand is difficult, therefore I have written a Python code for it, and I'll share that on your WhatsApp group as very simple Python code, which you can use to add more and more terms. And if you use 10 terms, we reach to an answer that is very close to the exact answer. In fact, it is exactly equal to the exact answer. So this is how we can use Taylor series method to find a solution for a given first order ordinary differential equations. That's all for this lecture. In our upcoming lectures, we'll study more about the numerical solution of ordinary differential equations. Thank you.